So now that we have a good handle on what the kind of pipeline hazards are and how they can be mitigated, let's look specifically at what those mitigation techniques actually look like. So in any case, for any kind of a pipeline hazard, the easiest and most guaranteed to work method is a stall, just waiting for the result to be ready, right? If we add two numbers together and we need that result before we do the next instruction, we just wait, right? We wait for the pipeline to finish before we start the next one. This is a bit of a waste, though, because those parts of the pipeline that are not functioning could have been used for useful work. And so we want to avoid that if we can, but we know this is going to work. And so the way we do this is called a pipeline bubble. Pipeline stall, pipeline bubble, more or less the same thing. And like imagining water in a pipe, if there is an air bubble that gets into that pipe, it just floats along like everything else, doesn't do anything useful, doesn't transport anything useful, but it flows in exactly the same ways. The bubble in the pipeline, same kind of a thing. And most instruction set architectures have a mechanism by which the assembler can insert a bubble into the pipeline if it knows that a data result will not be ready or a control result will not be ready before it's needed. So this is a no-op or NOP. And we can do this. Like, you can add a no-op into your program if you want a result to be done before the next result needs it. And this works, right? It works every time. But it wastes that instruction, right? The no-op does nothing when we could have done something. So instead, let's look at other ways to mitigate hazards to see if there's better things we can do than just waiting for the result to be ready. So let's look at branches. Again, the branch hazard happens when we have to make a choice about which instruction to accomplish, right? If we're making an if-then loop or going to a subroutine or something else, depending on the result of a branch choice, we might do instruction chain A or instruction chain B. How do we decide what to do? What can we do in this case? Well, there's a few different possibilities, right? Branches typically are used in two circumstances, well, lots of circumstances, but two that are primary: if-then choices and loops. Now, if-then choices, we can just guess, right? We call this speculative execution. We can just say, it's probably going to be the first one, or maybe just roll a dice and pick the first one, and just start executing that first one. Now, if we're wrong, we have to throw the result away and start again. But what's the harm in that, right? We would have had to throw no-ops away anyway. So we get a little bit of a performance boost if we can just start executing one chain instead of another. And it's important to recognize that if we get good at predicting which instruction chain we get, which instruction chain is correct, then we can optimize that kind of stuff. So branch prediction becomes this big thing people spend time on, because the better we can predict which branch we're executing, the better we can not waste pipeline execution stages. So that's for conditionals, for if-then situations. And then for loops, we can do another clever thing called loop unrolling. This is where if we have a loop that we know is going to be executed 4 times, we just make 4 copies of that loop in the instruction memory, right? Or even somewhere in the instruction cache, we can just have that loop execute 4 times by just feeding the same instruction 4 times. Unrolling means that there is no branch to choose, right? We do this, then this, then this. It's just the same instruction stream over and over again. And that works great if we know how many times the loop is going to execute, and if we have the space in instruction memory to do that. Sometimes when we compile, if we know the number of instructions or know the number of times through a loop, we can just unroll that loop 3 or 4 times, whatever, 100 times, and that becomes instructions in sequence in instruction memory. But if we have a loop that executes 1,000 times, and we put 1,000 copies of that loop in instruction memory, that's not going to work so well, right? That's going to be a waste of instruction memory. So now we have these different constraints lining up against each other. If we get lots of memory, no problem, but often we find ourselves trying to optimize code not just for how fast it works, but for how compact it is, right? Code compaction, code compression is a technique where we look at assembly instruction set architecture features and try to make our instructions smaller or fewer, right? Fewer instructions to make it fit into smaller amount of instruction space. And just as an aside, in modern assembly languages, there's sometimes even a technique of trying to make the instructions smaller. So ARM has this thumb variant, which instead of having 32-bit instructions, you have 16-bit instructions that happen twice, two instructions in one memory word to really compact the space that is required to store the program. Loop unrolling is completely the opposite solution, right? It balloons the space that we store, but the end result is that we don't have choices to make, and so we get better pipeline performance at the expense of instruction memory. And then with data hazards, we can further define this a little bit. We can look at the types of situations where we have data that we need, but it's not ready yet. There's actually 3 different kinds. Read after write, raw, write after read, war, and write after write, wow. These all happen in different circumstances. In simple pipelines, we don't get war and wah hazards. We primarily get raw data hazards, read after write. That means we write into a register file location and then immediately read it again, right? We can't do that because we have to wait for the write to be completed. That's 2 or 3 extra clock cycles before we can read that value. So read after write hazards for our simple pipelines are going to be the most common. And again, we have a couple of solutions, right? We can insert a bubble or we can forward data, and we'll look at data forwarding in a minute. Write after read instructions hazards and write after write hazards occur when we start to solve other problems in other ways. Remember, we said one of the ways that we can solve hazards is executing instructions out of order, right? If we have to wait for a resource to be ready, we can just execute unrelated instructions before we then execute the thing that had that requirement, that demand. But if we're not careful, executing out of order might cause us to write a value after we've written that value, and if we put them in the wrong order, then we get the wrong value, right? Or write a value after we've read it, even though we want to read the value that we should have written before. So there's a lot of circumstances where these other data hazards can appear, but for the most part, we're going to be looking at read after write hazards, right? And here is an example of what a bubble looks like, and then what a read after write hazard looks like. So if we are adding 2 numbers together, right? If we have this situation where we are adding 2 numbers into R0 and then reading from R0, we insert these bubbles, right? We have an instruction that is a no-op instruction. We have an instruction that is a no-op instruction. And these just, they sit and waste time with the intention that once the write is completed, in the next clock cycle, we can do the read, right? This is these sort of vertical idea of the pipeline. Others will sometimes produce figures like this, where the instruction waits for 2 bubbles and then completes after that. Same idea, except instead of looking at the pipeline as a whole, we look at individual instructions when we decide whether or not to insert bubbles. We can insert bubbles in a lot of different contexts. We can insert after writing a register, and then we have to wait for 2 clock cycles before we read that. We can either insert 2 bubbles, right, 2 no-ops, or 2 independent instructions, just like we were talking about. And the key thing with bubbles is to recognize that we're not losing time. There is no way, except with data forwarding that we'll talk about later, to solve the hazard, right? There's no way to get the result we need before it's ready. We can't go forward in time, except again with data forwarding. We have to wait for the result. So what do we do while we're waiting? We can do nothing. We can do something else. We can guess on what we might need to do and start doing that. But in all cases, we're not going to lose any time. We're still going to get the result as fast as we can. The thing we're optimizing for is effort, right? Do we waste time while we're waiting for a result, or do we do something useful when we're waiting for a result? And the other thing for high-level programmers to recognize is that these bubbles are going to be inserted automatically by the assembler or the compiler, and so be careful with your code. When you're writing code that has these kind of demands one after the other, keep in mind that bubbles are going to be executed, things are going to be issued out of order. The machine will take care of that for you. You'll get the right answer. But if you're careful with the code, you might be able to get answers faster.